The first talk we hear is given by Kwela from the University of Gdańsk, and he will speak about selective properties of ideals.
Okay, thank you. First of all, let me thank the organizers for giving me this opportunity to present my results. Yes, I will say a few words about various selective properties of ideals, and by ideals, I always mean ideals on countable sets, in particular on omega. So, okay, all the ideals considered in this talk are ideals on countable sets. I use this standard notation that given an ideal I by I plus, I denoted its co-ideal, and the members of the co-ideal are called I positive sets. Let me introduce the following three selective properties of ideals. First of all, an ideal is selective if for every partition of omega there is an I positive selector. And we only assume about this partition that it satisfies this condition that a finite sum of elements of this partition is not in the dual filter. This is the weakest assumption on this partition that we can make. Without this assumption, there will be no selective ideals. So this definition makes sense only with this assumption. But this is the weakest assumption that we can make. And of course, an ideal is selective if and only if its co-ideal is a happy family. So maybe I should call this property happy ideal or something like that, but I will stay with this name. Because I want to compare selectivity with other properties, in particular with weak selectivity. An ideal is weakly selective if, again, for every partition there is a selector not belonging to the ideal. But this time we additionally consider only those partitions with at most one element not belonging to the ideal. So a partition on the members of the ideal and one set does not have to belong to the ideal. And similarly, a third definition, an ideal is called locally selective if for every partition into elements belonging to the ideal there is an I positive selector. I've decided to, in this talk, to jump from one property to another, not to focus on one particular property and study it carefully. There are two reasons of that. First of all, I wanted to show the variety of these properties and to show that a slight difference in this definition can lead to completely different class of ideals. But the second reason is that, especially today, I should mention at least one result of Matthias, and therefore I need to talk about selective ideals. Okay, and it is from these definitions, it is very easy to see that every selective ideal is weakly selective, every weakly selective ideal is locally selective. And for maximal ideals, all the above coincide. So, and this is, it coincides with this happy ultrafilters from the previous talk. Okay, and firstly, I would like to focus on selectivity and mention a result of Matthias. In the case of definable ideals, selectivity and density exclude each other. This is this theorem, yes. And by dense ideal, I mean that in every infinite set one can find its infinite subset belonging to the ideal. This is density. Sometimes the term tall is also used. So by a result of Matthias, in the case of analytic or co-analytic ideals, selectivity and density exclude each other. Actually, they do not only exclude each other, but they are very far away from each other. And what I mean by far away, I mean two things. We, together with Piotr Zakrzewski, we investigated this distance, and we have two theorems. One of them, we called that this is this combinatorial distance, and the second one will be topological distance. Okay, so following Laflamme, we say that an ideal is omega diagonalizable if there is a countable family of infinite sets such that for each member of the ideal, one can find a member of this countable family disjoint from this member of the ideal. And if all this countable family is contained in some family A, then we say that the ideal is omega diagonalizable by this family A. And our result, joined with Piotr Zakrzewski, we assume that an ideal is analytic or coanalytic, and then it is selective if and only if it is omega diagonalizable by every ultrafilter contained in the co-ideal, and an ideal is dense if and only if it is omega diagonalizable by any filter on omega. So in part B we have any filter, in part A every ultrafilter contained in the co-ideal. So we see that selectivity is a much stronger property than non-density. And the second result, very similar, but in terms of topology. Okay, for each ultrafilter, we can assign the so-called ultrafilter topology on the family of all infinite subsets of omega. I don't want to define it strictly because it won't be important for me. I won't need this definition. But okay, there is some way of assigning topology to the ultrafilter. This was studied by Todorcevic, also by Louveau. And this is a slight modification of the Ellen-Tax topology. This ultrafilter topology is richer, it has more open sets. Okay, and our second theorem, again, we assume that an ideal is analytic or coanalytic, and then it is selective if and only if it is nowhere dense in the ultrafilter topology for every ultrafilter contained in the co-ideal, and an ideal is not dense if and only if it is nowhere dense in the ultrafilter topology for any ultrafilter. So again, in part B, there is only one ultrafilter, and in part A, all ultrafilters contained in the co-ideal. So again, selectivity is much stronger property than non-density. Okay, so there are no selective dense ideals, at least analytic or coanalytic ideals. And these two properties are very far away from each other. But what in the case of weak selectivity? Are there weakly selective ideals which are dense? And in fact there are, and even there is a quite big class of ideals satisfying these two properties. I will introduce this class. So suppose that we have a separable metrizable space X. It's a dense countable subset D and a sigma ideal J on X containing all singletons. Okay. And now we can define an ideal on D. D is countable. Okay. An ideal on D consisting of all subsets of D whose closure belongs to the sigma ideal. And we say that an ideal admits a topological representation if it is isomorphic to some ideal of the form I sub j. And the two well-known examples of such ideals. The first one is represented by on the 0-1 interval by the sigma ideal of Meager sets. The second one by the sigma ideal of Lebesgue null sets. And it is known that these two ideals are non-isomorphic. Okay, and this definition was introduced by Szabok and Zapp et al. And they gave the following conjecture, that an ideal admits a topological representation if and only if it is dense, F sigma delta, and weakly selective. Actually, the conjecture is only from B to A, because it is known that every ideal admitting a topological representation is dense, weakly selective, and F sigma delta. Okay, so the conjecture is from B to A. Okay, so it shows that there are quite many ideals which are both dense and weakly selective. We can forget for a moment about this F sigma delta assumption. And together with Marcin Szabok, we tried to prove this conjecture. We didn't manage to do it, but we have a slightly different characterization of ideals admitting a topological representation. And no, for this characterization, I will need the following definition. We say that an ideal is countably separated if there is a countable family such that for any two sets, one set A not belonging to the ideal, second set B belonging to the ideal, there is one member of this countable family which is disjoint from B and intersects A on a big set in the sense that the set doesn't belong to the ideal. Okay, and this is stronger than weak selectivity. Each countably separated idea is weakly selective. Maybe it is not obvious now, but it is quite easy to prove it. And our characterization is as follows. An idea admits a topological representation if and only if it is dense and countably separated. So here we have one advantage, because we don't need this assumption that the ideal is F sigma delta. We don't say anything about its descriptive complexity. This is a purely combinatorial characterizations of ideals admitting a topological representation. But we still don't know if this conjecture of Szabok and Zapp et al. Is true. About the descriptive complexity, we proved the following, that an analytic ideal which admits a topological representation always has to be F sigma delta complete. Okay, and what is with this weak selectivity assumption? We only managed to prove the following characterization of weakly selective ideals. An ideal is a co-analytic ideal, is weakly selective if and only if it is an intersection of a family of ideals admitting a topological representation. So it's weaker than this conjecture of Szabok and Zapp et al. And I would like to focus for a moment on the proof of this theorem. Actually, not only on the proof, but on the idea behind this proof. The idea is to consider the following infinite game related to an ideal. This game is actually the same game as in the previous lecture, but there was an ultrafilter. Okay, this game was assigned to an ultrafilter, and here we can have only an ideal, not necessarily a maximal ideal. So again, player one picks in his nth turn, he picks some elements of the ideal, and the second player responds with points not belonging to this set picked by player one. And player one wins if this set of all points picked by the second player is in the ideal, otherwise player 2 wins. This game was, later. By Martin's theorem on Borel determinacy, this game is determined, so one of the players has a winning strategy. And this game was studied by Laflamme. He gave some characterizations of winning strategies. So he proved that player 1 has a winning strategy in this game if and only if the ideal is not weakly Ramsey. What I mean by weakly Ramsey, it will be later. For now on, you just need to know that there is such property called weakly Ramsey. Okay, and it can be shown that weak selectivity implies weak Ramseyness. So player 1 cannot have a winning strategy. The game is determined, so player 2 has to have a winning strategy in this game. And again, by Laflamme's characterization of this game, we know that the ideal has some nice combinatorial properties. In fact, it is omega diagonalizable by its co-ideal. This is a very nice property. And it allows us to continue this proof. There are still some quite difficult calculations to make, but the idea is, as I said. Okay, and now this weak Ramseyness. This is a third selective property which I want to discuss. Okay, here I repeat the definitions of weakly selective ideals and locally selective ideals. And let's look for a while on the definition of weakly selective ideals. We can consider a slight modification of this definition. In the original definition, we have a partition satisfying some things, and with at most one element not belonging to the ideal, and then we look for an I-positive selector. So now, in this proposition, we have the first part is the same. We have a partition with at most one element not belonging to the ideal and satisfying this technical property. But the second part is different. We search for the selector, enumerate this selector, and this is increasingly enumerate, and this is this function f. We want to that this selector does not belong to the ideal, so f of omega does not belong to the ideal. But additionally, we require that this technical property from this last line of the proposition. So f of n plus 1 must be in the union of all xi's for I greater than fn for each n. Okay. Something like that. Okay, and Grigoriev proved that this a little bit changed definition is equivalent to the original definition of weak selectiveness. Okay, and we can do the same with the definition of local selectiveness. So we can define such property that an ideal is weakly Ramsey if every partition into elements belonging to the ideal, for every partition into elements belonging to the ideal, there is a strictly increasing function with range not in the ideal, and such that it satisfies this property, technical property. Okay, and from this, we can see that weak Ramseyness is between weak selectiveness and local selectiveness. So every weakly selective ideal is weakly Ramsey, and each weakly Ramsey ideal is locally selective. But what is surprising is that actually weak Ramseyness is not equivalent to local selectiveness. So, okay, I said already all of that. Okay, so the implications cannot be reversed. So there is a locally selective ideal which is not weakly Ramsey. These properties are very close to each other. It's hard to find such ideal. All known examples do not distinguish these two properties, but I found one example. And actually I did a little bit more, because I characterized this property, this weak Ramseyness, in terms of catheta of order and in terms of containing an isomorphic copy of an ideal. So I write that the ideal I is below J in the catheta of order if there is a function such that preimages of elements of the ideal I are in the ideal J. And if additionally F is a bijection, then we say that the ideal J contains an isomorphic copy of the ideal I, and write this square inequality. Okay, and I proved that there is a critical ideal, critical in the sense of these two partial orders on ideals, a critical ideal for weak Ramseyness. So there is an ideal, I called it WR ideal, such that for any ideal I, the following are equivalent. I is weakly Ramsey, I is not above WR in the catheta of order, and I does not contain an isomorphic copy of the WR ideal. And if moreover our ideal is coanalytic, then the above three conditions are equivalent to the fourth one, saying that the ideal is omega diagonalizable by its co-ideal. This is this nice property which I mentioned a few minutes ago. This nice property, it is okay. Let's read it. There is a countable family of members of the co-ideal such that each member of the ideal is disjoint from some member of this countable family. I think it's very nice, and in fact this property was used by many authors already. Of course, okay, this is also equivalent to saying that in this game where I have it. Okay, in this game player 2 has a winning strategy. Okay, so there is a fifth equivalent condition that player 2 has a winning strategy in this game considered a few minutes ago. And this game was used at least 3 times. I know about 3 applications of this game. First application is this, what I mentioned before, this our proof of this characterization of weakly Ramsey ideals. The second application is the proof of Hruszak's category dichotomy. He used exactly the same game, but I think he didn't know that already Laflamme characterized it. And the second application, actually a whole class of applications, is connected with ideal convergence of sequences of functions. Maybe some of you know that there is such thing as ideal convergence. And we can consider bare classes related to ideal convergence. And in the studies of these bare classes connected with quasi-continuous functions, this ideal also appears to be critical. So an ideal behaves more or less like ideal convergence behaves more or less the same as classical convergence in the case of quasi-continuous functions, if and only if this ideal WR is not below I in the catheta of order. Okay, so this game has many applications, and that's all I wanted to say. My talk was based on three 3 papers. All of them are available on my website. Thank you.
Are there any questions?
Is WR definable?
Yes, of course. It's a subsigma.
It's a sigma.
Yes, it is quite okay. The definition has 2 lines. It is quite short, but to understand it, we would need, I don't know, 2-3 minutes. I didn't want to introduce it.
Second, you had this theorem about selective being intersection of a family of topologically representable
Yes.
ones. Do you have, under some circumstances, some estimate on the size of that family? Like
This
countable
size
family,
is
Omega
the
one?
size. Oh no. For each member of the ideal, there is
Sure.
an ideal which in this
But
intersection.
do you
So
have some estimate, some better estimate?
no, I don't have anything.
Are there some other questions? Then let's thank the speaker again.